Okay, so now all we have to do is simplify this character that we figured out for the C5 operation or the C5 to the 2C5 class. It helps here to just use some trigonometric relationships, fairly complicated ones, not common ones, for the 72-degree and 144 degrees. So I'm going to write down the ones that we're going to need to simplify this. And they are cosine 2 pi over 5 is actually equal to, it turns out, root 5 minus 1 over 4. And then there's another one, which is sine, this one's even crazier, sine of 2 pi over 5 equals the square root of 5/8 plus the square root of 5 over 8. And then the last one that we're going to need at the end is cosine of 4 pi over 5 is actually equal to negative quantity root 5 plus 1 over 4. So at this point, it's just going to turn into a big mess of algebra to simplify all these things, but let's just do it so we can get a nice answer in the end. So we sub in the cosine 2 pi over 5 here, and so we get root 5 minus 1 over 4 squared times 2, and then we also sub in this one. We're squaring this sine 2 pi over 5 term, so that square root, that big square root, just goes away. So I'm just gonna write that term without the square root. Okay. And then we have to FOIL out this square root 5 minus 1 term. We have the 2 in front. When we FOIL that, we get 5 minus 2 square root 5. Those are inside terms, plus 1 over 16. And then this 2 times 5/8, that's 5/4. And 2 times negative 2 times square root of 5 over 8 is negative square root of 5 over 4. And so we keep going here. At this point, we can change 2/16 to 1/8, and then divide by 8 and split up the terms. So we're going to get 5/8. We have another 2 here, so that's going to end up being minus square root 5 over 4. And then we have a 1 there, so that's 1/8, and minus the rest of our terms, 5/4 and square root 5 over 4. And so what that is going to mean is that it is going to equal 5/8. Sorry, so now we have 5/8 plus 5/8 plus 1/8. So that equals 6/8, which equals 3/4. So 3/4 minus 5/4 over there, and then minus 2 root 5 over 4. These terms are the same. And so that ends up equaling 2 times negative root 5 plus 1. Because we have a negative 1/2 here. And so actually going to be a negative 2 on the outside, sorry. Negative 2 on the outside. So that gets us this term, that gets us negative 1/2, a negative 1/2 when we divide all this by 4. So negative 2 times root 5 over 4, that's this term, and then we get negative 2 over 4, that's the negative 2/4, negative 1/2. What is that equal to? Well, that's why I gave us this term up here. That's just actually 2 times cosine 4 pi over 5. And that is actually our answer for the character of the C5 operation. So a lot of work there to just get to that point. But now we can go back to what we had written earlier, and we can actually write that in. So we figured out that character. 2 cosine 4 pi over 5. Okay, the very nice thing about this is if we go back to this and we think about, all the work that we did to figure out pi of C5, we were doing all this using, starting from the rotation matrix, which was cosine 2 pi over 5, because we're doing a C5, minus sine 2 pi over 5, cosine 2 pi over 5 on the diagonal, and sine 2 pi over 5. So that's where it all started from, and then we're plugging in for, remember, x, y, and x squared minus y squared. We figured out that those two quadratic functions transform together. That was for C5, right? We did that for the C5 operation. However, we can now just do the exact same thing, but for the C5-2 operation. And fortunately, we don't have to redo all of our work, because this is going to be exactly the same math, but all of the 2 pi's over 5's that we had in the previous video, where we did all that work factoring out xy and x squared minus y squared, all of that is going to end up the same. And so our final answer for the character is just going to be chi C5 squared now, 2 times, equals the exact same thing, but now with 4 pi over 5, because we're doing 144-degree rotation, instead of a 72-degree rotation. And so we can write that out here, that it's just 2 cosine squared over of 4 pi over 5 minus 2 sine squared 4 pi over 5. Now, again, this doesn't look too nice, and as you might imagine, you can simplify this. We do need to know some other relationships here. And so the other relationship we need to know, I'll write it in a different color, is the sine of 4 pi over 5. What does that equal to? And that ends up equaling to something quite similar to the sine of 2 pi over 5, except we have a minus sign. So it's square root 5/8 minus square root 5 over 8. Okay, so again, this is very similar, now just simplification. And it turns out what this ends up equaling to, I'll go through it, is, well, we sub in cosine squared 4 pi over 5. We have that over here. We factor it out. We keep the 2 that we have, and we get 2 root 5 plus a 5, okay, over 4. Sorry, no, over 16. Over 16. And then we do the sine squared part, where it's just this quantity squared. So this one's a little bit simpler to do. Just 2 times 5/8 minus the square root 5 over 8. And then we get, if we go over here, 1/8, 2 divided by 16, plus a root 5 over 4, because we have 2 2's there, 2 and 2, divided by 16, and then plus 5/8 term, 10/16, which is 5/8. And then we have our second term over here, that's going to become minus 10/8 and minus, and plus, actually, -2 times a negative, plus root 5 over 4. That whole thing equals, we have -8 plus 5/8, that's -4/8 minus, sorry, that's 6/8 minus a 10/8, which is a -4/8, which is minus 1/2. And then we have root 5 over 4 plus root 5 over 4, which is root 5 over 2. And so that whole thing ends up equaling 2 times, we can factor out a 2 now, 2 times -1 plus root 5 over 4. And so what that is, if we go back to our relationships up here, is actually the same thing. I just wrote it backwards, but root 5 minus 1 over 4 is right here. So that's cosine 2 pi over 5. And so miraculously, this just simplifies to 2 cosine 2 pi over 5. And that is our chi for our C5 operation twice simplified. So now we can go back to what we wrote, and we can fill that in to our character table. 2 cosine 2 pi over 5. So interestingly, these terms just flip-flop, and all the math is gonna work out. These are all gonna be orthogonal to each other, all these different vectors. We just have this last component to figure out, and that's gonna be sigma v. And so if we go back to what we've talked about in the past, in previous videos on this derivation, and we have our pentagonal pyramid. We have our z vector, of course, defined as the principal rotation axis. We have our x vector for ease being defined as going through one of the bonds. And we have our y vector coming out towards us. We could make it a wedge if we want to signify that. And so we have our little, our plane here. And so one of our mirror planes, our vertical mirror planes, is going to contain that x vector because we define the x vector as being in the mirror plane. So so now we can think about how x and y transform for all these. Of course, we have to do x, y, and x squared minus y squared, but for review, we have to do x and y first, so then we can derive those. We've done x and y previously in another video that got us up here. It got us this character, but let's just go through it so we can have it all together on one page. So x, of course, is going to go x with identity, y goes to y. That's not that interesting. So x, y, obviously those are going to go to the identity matrix. They're just going to go to themselves. So we can write that for sigma v, but we're doing this for identity here. But really what we care about, of course, is sigma v. Okay, so let's see about sigma v. That's the one we have to do. This is just kind of reviewing how we got a character of 2 up here. Okay, let's do the character of sigma v. It's going to be pretty simple, just going back to basics here. No trigonometry, no crazy trigonometry, because x goes to x because the x vector is in this mirror plane, and y is looking at itself in the mirror plane, so y goes to y. Y goes to negative y. So now, what does xy go to? Well, x went to x and y went to negative y. So y goes to x times negative y, which is negative xy. So the character is going to be, for that part, is going to be a negative 1, right? But we know these transform together, so we have to also consider x squared minus y squared. We know x squared minus y squared and xy transform together. And so x went to x, that's going to stay x squared. Y went to minus y, so we're going to plug that in for y there. But that's going to get us x squared minus y squared. So we're going to end up with our 2 by 2 matrix very simply here. This is the fun, easy part. Goes to, and I like this one a lot more than the crazy cosines, what 2 by 2 matrix takes us to negative xy and x squared minus y squared? Well, that's just 1, 0, 0, negative 1. Then we take the sum of the diagonals to get the character. And so our character is just going to be, for sigma v here, it's just going to be 1 plus negative 1, which is 0. So we get a 0 here. So at this point, we have derived the complete character table. We had to do some crazy functions here to get this to work. The only thing left is to assign the Mulliken symbols, and that is super easy in comparison to everything we just did. You can see that we indeed did get the right answers here. We solved for how x and y transform. We solved for how x squared minus y squared and xy transform. You can see that there's these other more complicated cubics. Those are just these times z for the most part, except for this one, which would really be some terrible math. But these z's are just times minus 1. So those are easy to figure out. The only thing left was to talk about the Mulliken symbols here. And this doesn't take too much time to explain. We have dimensionality of 1 here, so they get values of A or B. Why are they A's? Because they're symmetric, they're both symmetric with the principal rotation axis. If these were negative ones here, we'd have to call them B's. And then we're giving it a subscript 1 and a 2 respectively because we are symmetric and anti-symmetric with respect to the mirror plane. And then same sort of thing here with the E's. They're E's because of the Mulliken symbols. And then this part, there aren't really well-defined rules of whether, what you call 1 and what you call 2. So you just have to use convention here. And so this one ends up being called 1. Usually that will be for sort of the simpler function that describes it. But you can see they're both actually zeros here for the mirror plane, so you can't use that rule. And then these values are weird. So this one's sort of, not intuitive. So you just got to look up the character table if you want to use the same convention as other people. This is just a naming thing, right? So it's just a way of making sure chemists are on the same page with one another.